A cosmic metropolis floats in deep space, home to thousands of galaxies. This is the Hercules Cluster, a place where the normal rules of the universe seem to break down. We are about to journey through 25 of its most baffling secrets. You will discover phenomena that challenge everything scientists thought they knew about dark matter, gravity, and the birth of galaxies. How can an entire galaxy exist without the invisible glue that supposedly holds it together? What is the true nature of a ghostly radio whisper that fills the void between worlds? The answers we find here could rewrite our cosmic textbooks. What single cosmic mystery would you most want to solve? Our very first mystery strikes at the heart of modern astrophysics. Deep within the Hercules Cluster, astronomers found a galaxy that simply should not exist. It is a galaxy that appears to be missing its dark matter. This invisible substance is the cosmic scaffolding for every galaxy we have ever observed. It is the unseen gravitational glue that prevents spinning galaxies from flying apart. Without it, a galaxy's stars should be scattered across the void. Yet here one is, a seemingly normal collection of stars, defiantly holding itself together. The galaxy, known as NGC 6052, was studied using the Hubble Space Telescope. Scientists measured the motions of its stars, expecting to see the telltale signs of dark matter's immense gravitational pull. Instead, they found something astonishing. The stars were moving at speeds that could be explained by the gravity of the visible matter alone. There was no need for dark matter and no evidence of its presence. This single observation sent shockwaves through the scientific community. How could a galaxy form without the very ingredient we thought was essential? One theory suggests a violent galactic collision within the crowded cluster might have ripped the dark matter away from the stars. Another, more radical idea is that our understanding of gravity itself is flawed and needs a fundamental rewrite. This galaxy is not just a cosmic oddity, it is a profound challenge, forcing us to question if we have been wrong about the universe's most basic building blocks all along. The mystery of missing dark matter is not the only ghost in this cosmic machine. Within the same crowded neighborhood, astronomers have found entire galaxies that are almost invisible. These are the ultra-diffuse galaxies, cosmic phantoms as wide as our own Milky Way, yet containing only a tiny fraction of its stars. Picture a city the size of London, but with only a handful of streetlights scattered in the vast darkness. That is the scale of this emptiness. These galaxies are so faint and spread out that they blend almost perfectly into the blackness of space, which is why they remained hidden for so long. Their discovery was a happy accident, made only when telescopes became powerful enough to detect this incredibly faint, smeared out starlight against the backdrop of the Hercules Cluster. What is truly baffling is not just their existence, but their location. The core of a galaxy cluster like Hercules is a brutal environment, filled with searing hot gas and powerful gravitational tides that should shred fragile, wispy galaxies. It is a cosmic demolition derby, yet these ultra-diffuse galaxies are not only present, they appear to be surviving. How can something so delicate endure in a place so violent? This resilience is a major part of the puzzle. One leading theory suggests they are failed galaxies, islands that formed with immense amounts of dark matter protecting them, but for some reason, their star formation never truly ignited. Their dark matter halos act as protective shields, allowing them to withstand the cluster's chaos. Another idea proposes a more tragic history, that they are the shredded remnants of once normal galaxies, their outer stars torn away by gravitational interactions, leaving behind only their dense, protected cores. Their survival forces us to rethink the very definition of a galaxy. It seems that a vast collection of stars is only one possible outcome. The universe, it appears, can also build giants of pure shadow and whisper, challenging our assumptions about what is strong and what is weak in the cosmos. And if galaxies can be this ghostly, what other faint, unseen structures might be hiding in plain sight? But the ghostly galaxies of Hercules are only small pieces in a puzzle of staggering proportions. Beyond the cluster itself, astronomers have mapped a structure so vast it challenges the fundamental rules of the cosmos. This is the Hercules-Corona Borealis Great Wall, a colossal filament of galaxies that may be the single largest object we have ever observed. To grasp its scale, you must first forget everything you know about distance. Our own Milky Way galaxy is 100,000 light-years across, a size so immense it defies human comprehension. The Hercules Cluster is over 10 million light-years wide. The Great Wall, however, stretches for an astonishing 10 billion light-years. It is a cosmic continent, a web-like structure containing billions of galaxies all bound together by gravity. Its discovery was a profound shock. According to the cosmological principle, a cornerstone of modern astronomy, the universe should look roughly the same in every direction when viewed on a large enough scale. Matter should be distributed fairly evenly, like raisins in a rising loaf of bread. The existence of the Hercules-Corona Borealis Great Wall directly contradicts this. It is a glaring irregularity, a lump in the cosmic batter so enormous that it seems to break the rules. How could such a structure form in the relatively young universe? The timeline does not seem to add up, as there may not have been enough time since the Big Bang for gravity to pull together something on this scale. This has sparked a fierce debate among cosmologists. Is the Great Wall truly a single, connected structure, or is it a trick of perspective, a chance alignment of separate galaxy clusters that only appears connected from our viewpoint? Its very existence forces a difficult choice. Either our models for how large-scale structures form in the universe are incomplete, or our foundational principle of a uniform cosmos is wrong. This is not just a debate about size. It is a question about the blueprint of reality itself. If the universe is not smooth, what other impossible structures are waiting to be found? While the Great Wall challenges our view of the cosmos on the grandest scale, a far more subtle and invisible energy haunts the heart of the Hercules Cluster itself. A ghostly radio halo, an immense cloud of radio waves, permeates the cluster's core. This is not a structure you could ever see with your own eyes. It is a faint, whisper-thin veil of energy, detectable only by the most sensitive radio telescopes. This halo is not coming from any single galaxy, but from the seemingly empty space between them. It is a signature of the cluster's violent past, a cosmic echo of ancient chaos. The energy for this vast emission comes from electrons, accelerated to nearly the speed of light, spiraling through powerful magnetic fields that are tangled throughout the cluster's core. These particles are so energetic that when they interact with the magnetic fields, they emit radio waves across the void. The presence of this halo is a direct clue that the Hercules Cluster is not a quiet, settled place. It is the product of a colossal merger, a catastrophic event where two or more smaller clusters smashed together in the distant past. Think of it like the lingering heat and sound after a massive thunderstorm. The collision would have sent immense shock waves rippling through the cluster's gas, compressing magnetic fields and accelerating particles to these incredible speeds. The radio halo is the long-lasting remnant of that cosmic tempest. Yet, a piece of the puzzle remains missing. The sheer size and power of this halo are difficult to explain completely. The shock waves from the initial merger should have faded by now, and the particles responsible for the radio emission should have lost their energy. So why is the halo still so bright? There must be a continuing source of energy, a process that is continually re-accelerating these particles, keeping the ghostly cloud alive. This points to ongoing, low-level turbulence within the cluster, a simmering violence that continues to stir the cosmic pot long after the main collision is over. The invisible halo is more than just a remnant. It is a living testament to the dynamic and explosive life of a galaxy cluster, and its enduring energy hints at forces we are only beginning to understand. This invisible turbulence is not the only force pulling the strings. On a scale even larger than the cluster itself, astronomers have detected a motion that defies all conventional explanation. Entire galaxy clusters, including the immense Hercules Cluster, appear to be streaming in a coherent direction, as if pulled by a cosmic current. Scientists call this the dark flow. It is not the gentle drift of the universe's expansion, but a peculiar velocity, a directed movement that points toward a specific region of space for which we have no obvious cause. The evidence for this startling motion comes from a faint, ancient light that fills the entire cosmos, the cosmic microwave background. This afterglow of the Big Bang serves as the ultimate frame of reference, a fixed backdrop against which the motion of all structures can be measured. By studying tiny temperature variations in this light as it passes through moving galaxy clusters, researchers found a consistent statistical drift. It is as if thousands of ships, scattered across a vast ocean, were all being pulled by a single, unseen tide. The implications are staggering. The gravitational pull of all the known matter in the observable universe cannot account for this motion. So what is doing the pulling? The debate surrounding dark flow is intense. Some scientists propose a truly radical idea that the source of this gravitational tug lies beyond the horizon of our observable universe. This would mean our cosmos is just one bubble in a much vaster multiverse, and the gravitational influence of an external, unseen mass is reaching us. Others remain deeply skeptical, arguing that the statistical analysis is flawed or that unknown local effects are creating an illusion of motion. The controversy cuts to the very core of cosmology. If the dark flow is real, it hints at a reality far grander and more complex than we ever imagined. A cosmos where our entire observable universe is just a small part of a much larger structure. But if it is an illusion, it forces us to question our most fundamental tools for measuring the cosmos. Is Hercules, and everything we can see, truly sailing toward an unknown shore, or are we simply misreading the map? An even greater gravitational paradox hides within a single galaxy inside the Hercules Cluster. At its core sits a supermassive black hole of such staggering proportions that it defies all expectations. This cosmic leviathan is simply too big for its galactic home. Scientists have a well-established rule of thumb, a relationship between the mass of a galaxy's central bulge of stars and the mass of its central black hole. In a stable, mature galaxy, these two masses should be in balance, like a perfectly weighted pendulum. But here, the black hole is overwhelmingly massive, a giant inhabiting a house built for a much smaller occupant. To weigh this invisible object, astronomers did not look at the black hole itself, for no light can escape it. Instead, they observed the frantic dance of stars whipping around the galactic center. Using the Hubble Space Telescope, they measured the velocities of these stars with incredible precision. The faster the stars were hurtling in their orbits, the stronger the gravitational pull at the center had to be, revealing the immense mass of the unseen anchor holding them all in its grip. The numbers they calculated were shocking. This black hole is tens, perhaps even hundreds of times more massive than the standard model predicts for a galaxy of this size. Its existence throws a wrench into our understanding of how galaxies and their black holes grow up together. The prevailing theory suggests they co-evolve, with the galaxy feeding the black hole, and the black hole, in turn, regulating star formation through powerful outbursts of energy. So how did this one grow so powerful while its host galaxy remained relatively modest? One possibility is a dramatic and ancient feeding frenzy. Perhaps this black hole gorged itself on vast quantities of gas and dust during the cluster's violent early history, growing to a colossal size before its galaxy had finished forming. Another, more chaotic scenario involves a galactic merger, where the black holes from two colliding galaxies spiraled together and merged, creating a single, supersized gravitational monster. This overmassive black hole is more than just a cosmic anomaly. It is a direct challenge, forcing us to question if the relationship we thought was universal is merely a suggestion, and that the universe has far more dramatic and violent ways to build its most mysterious objects. What other rules of cosmic growth might be broken in the chaos of the cluster? Gravity itself can paint a ghostly portrait in the void. Astronomers mapping the Hercules Cluster observed a signature in the fabric of space, so strange it seemed to sketch a perfect circle of nothing. This was the ring of dark matter, an invisible structure revealed not by light, but by the way it warps the light from galaxies far behind the cluster. The technique used to find it is called gravitational lensing, a powerful cosmic tool that relies on a prediction from Einstein's theory of general relativity. Massive objects, like galaxy clusters, bend the fabric of space-time around them. This warping acts like a lens, distorting and magnifying the light from more distant objects that happens to pass through this region. By carefully measuring these subtle distortions in the shapes of thousands of background galaxies, scientists can create a map of the cluster's total mass, including the vast amounts of invisible dark matter that would otherwise remain completely hidden. When they created this map for the Hercules cluster, they saw something extraordinary. The dark matter was not distributed in a smooth, featureless cloud. Instead, the data revealed a distinct, ring-like structure, a perfect circle of gravitational influence, separate from the visible galaxies and hot gas. It was as if they had drawn the outline of a phantom, using only the bending of light. The initial discovery sparked immediate questions. How could such a perfect, isolated ring form? The leading theory points to a colossal collision. Picture two smaller clusters smashing together in a catastrophic event billions of years ago. As they pass through one another, their clouds of dark matter, which respond only to gravity, would have sloshed outward. Much like a ripple expanding on a pond after a stone is thrown, the dark matter could have separated from the regular matter and coalesced into this temporary, ring-shaped structure. This would make the ring a fleeting cosmic fossil, a snapshot of a violent past event. However, the mystery only deepens from there. The ring appeared to be offset from the cluster's center, and its longevity is a major puzzle. Simulations suggest such features should dissipate relatively quickly, yet this one seemed to persist. Is the ring a true, stable structure, revealing a new and unexpected way that dark matter can clump and behave? Or was its detection a momentary glimpse of a fading echo, a ripple that we were just lucky enough to catch before it vanished forever? The ring challenges not only our ability to map the invisible, but also our understanding of its fundamental nature. Is dark matter capable of forming such intricate, temporary architecture in the aftermath of cosmic violence? The answer lies written in the distorted light, a secret circle waiting to be fully decoded. These phantom rings and cosmic ripples are not the only signs of a violent history. The Hercules Cluster is also a graveyard, home to galaxies that have met a strange and quiet end. One such galaxy appears to have died prematurely, its vibrant life of star formation snuffed out long ago. Astronomers classify it as a red and dead galaxy, a cosmic fossil frozen in time. Its population of stars is aging uniformly, glowing with a dull, red hue, with no brilliant blue sparks of newborn stars to break the monotony. It is a place where stellar birth has ceased completely, and the question is, why? What cosmic process could be so efficient, so thorough, that it completely extinguishes a galaxy's ability to create new suns? The leading suspects are two brutal mechanisms tied to the cluster's harsh environment. The first is a process called ram pressure stripping. Picture a galaxy, rich with the cold gas needed to form new stars, plunging at high speed through the superheated plasma that fills the space between galaxies in the cluster. This thin, incredibly hot gas acts like a ferocious cosmic wind. As the galaxy moves, this wind violently blows away its reservoirs of star-forming fuel, much like the wind stripping leaves from a tree. The galaxy is effectively stripped bare, its future stolen in a relatively short, dramatic event. The second, more gradual process is known as strangulation. This is a slower, more insidious death. Here, the galaxy is not violently robbed of its gas, but instead, its supply of fresh, external gas is cut off. Every galaxy needs to accrete new gas from intergalactic space to continue forming stars over billions of years. As a galaxy falls into the dense core of the Hercules Cluster, the immense gravitational pull and the hot intracluster gas can prevent this replenishment. The galaxy continues to consume its existing fuel, but with no way to restock, it slowly starves. Its star formation rate dwindles over time until it finally, quietly, winks out. The mystery of this particular red and dead galaxy is the sheer completeness of its demise. The process was not partial, it was absolute. This suggests it experienced a perfect storm of cluster violence, perhaps a combination of both ram pressure stripping and strangulation acting in concert. Its location in the cluster, its trajectory, and the timing of its arrival all conspire to create a cosmic kill zone of unprecedented efficiency. This galaxy stands as a silent monument to the forces that govern life and death on an unimaginable scale, a stark reminder that even in the vastness of space, environments can be lethal. These silent stellar streams are the ghosts of ancient meals, stretching for millions of light years between the bright galaxies of the Hercules Cluster, are immense, faint rivers of stars known as tidal tails. They are the cosmic evidence of galactic cannibalism, the shredded remains of smaller galaxies that were torn apart and consumed by larger neighbors. You cannot see them in a typical telescope image, as their light is incredibly dim, 1,000 times fainter than the darkest night sky we perceive from Earth. Their discovery required the most sensitive deep imaging surveys, which slowly accumulated their faint starlight to reveal these sprawling, ethereal brushstrokes across the void. Each stream is a fossilized record of a single, violent act. Computer simulations allow us to rewind the cosmic clock and watch these ancient collisions unfold. The process is one of pure gravitational chaos. As a smaller galaxy swings too close to a more massive one, the difference in gravitational pull between the near and far sides of the victim becomes overwhelming. This tidal force stretches the smaller galaxy, pulling it apart like cosmic taffy. Some stars are flung out into long, streaming arcs, while others are absorbed into the larger galaxy, making it grow even more massive. These simulations show the intricate shapes the tails can take, from great loops to straight, needle-like filaments, all depending on the angle and speed of the original encounter. The true mystery, however, lies in what we cannot yet see. The known tidal tails are likely just the brightest and most obvious examples. How many more of these faint streams crisscross the cluster, tracing a history of violence we have not yet mapped. Each tale represents a single merger, and by counting them, astronomers hope to piece together the full story of how the Hercules Cluster built itself up over billions of years. But the faintest streams remain invisible, meaning our current tally of this ancient carnage is almost certainly incomplete. We are left with a profound question. Are we looking at the aftermath of a handful of major collisions, or is the cluster's history written in countless faint streams, a web of destruction so complex we have only just begun to trace its outlines? Gravity can bend light into a mirage, and in Hercules, one such mirage shines with a peculiar brilliance. Among the many distorted images of background galaxies, a single lensing arc stands out, not just for its brightness, but for its defiance. This immense, curved smear of light is the magnified and contorted image of a far more distant galaxy, projected across space by the cluster's immense gravitational field. According to our best maps of the cluster's dark matter, this arc should appear in one specific place and with a certain brightness, yet the reality is slightly, but undeniably, off. Its position is a fraction askew, and its magnification is just a bit stronger than the models predict. It is as if a powerful magnifying glass was held up to the cosmos, but the lens itself has a tiny, unseen flaw. This small anomaly is a big problem for our understanding of the invisible universe. The dark matter models used to predict these lensing effects assume the matter is distributed in a relatively smooth, predictable halo. The mismatch with this particular arc suggests that the dark matter scaffolding of the Hercules cluster is not perfectly smooth at all. Instead, it might be clumpy, filled with invisible lumps and subhalos that the models do not account for. Think of it like looking at a disturbed pond. If the surface were perfectly smooth, the reflection of a tree would be clear and precise. But if there are unseen currents and ripples beneath the surface, the reflection becomes warped in unexpected ways. This lensing arc is that warped reflection, and the unseen ripples are the hidden substructures of dark matter. What could these invisible clumps be? They might be the remnants of devoured dwarf galaxies, their stars long since scattered, but their dense, dark matter cores still holding together, orbiting silently within the larger cluster. Their concentrated gravity would act as tiny additional lenses, subtly enhancing the magnification and shifting the arc's position in a way that a smooth model cannot replicate. This single, bright arc is therefore more than a beautiful cosmic accident. It is a forensic clue, pointing toward a richer, more complex architecture of dark matter than we ever imagined. If dark matter can form these invisible islands, it means its nature is far from simple. Could it be that we are not just mapping a single phantom, but an entire hidden population, their presence revealed only by the slight warping of a distant galaxy's light? The violence within the Hercules cluster can forge monsters, but it can also create cosmic projectiles. Some galaxies are not merely drifting, they are being violently flung away from the cluster's core at speeds so high they defy easy explanation. These high-velocity ejections are the cluster's way of expelling its own members, a gravitational slingshot on an unimaginable scale. The primary engine for this celestial catapult is a process known as a three-body interaction. Picture a chaotic dance involving three galaxies, not a gentle waltz, but a frantic, close-quarters scramble. As they swing past one another in the cluster's dense core, their gravitational fields interact in a complex tug of war. Through this chaotic exchange, one of the galaxies can be flung outwards at tremendous speed, receiving a gravitational kick that sends it racing toward the cluster's outskirts, while the other two galaxies might be sent spiraling inward, their energy transferred to the escaping object. It is a cosmic game of billiards where the balls are entire galaxies. The question then becomes one of ultimate escape. Is the galaxy's newfound velocity enough to achieve freedom? The answer depends on a simple cosmic equation, a battle between kinetic energy and gravitational potential. The galaxy's speed gives it the kinetic energy to fly away, but the combined gravitational pull of every star, every galaxy, and every ounce of dark matter in the entire Hercules cluster acts as a powerful anchor, trying to drag it back. For most of these ejected galaxies, the outcome is a life in exile, not true freedom. They will soar out to the very fringes of the cluster, reaching incredible distances, only to eventually slow, stop, and fall back in, like a stone thrown high into the air that is inevitably pulled back to Earth. They become part of a population of high-speed galaxies on immense, eccentric orbits, forever bound to the cluster that expelled them. Yet, the most tantalizing possibility remains. Could a galaxy receive such a perfect, powerful kick that it is flung out with enough speed to overcome the cluster's entire gravitational grip? In theory, yes. A galaxy could achieve escape velocity, breaking free from the Hercules cluster entirely to become a true intergalactic wanderer, a lone ship sailing the dark ocean between galaxy clusters. We do not yet know if any of the galaxies we see are on such a one-way journey. Their trajectories are subtle and difficult to measure with absolute certainty over such vast timescales. Each high-velocity galaxy we spot is a testament to the raw power of gravitational dynamics. They are living proof that the cluster is not a static collection of islands, but a dynamic and often violent system, capable of both creating and destroying, of building up immense structures and then hurling its own pieces into the void. Deep within the searing heart of the Hercules cluster, another invisible boundary defies the laws of physics. The space between galaxies is not a true vacuum. It is filled with a superheated plasma, a thin gas burning at tens of millions of degrees, so hot it glows not in visible light, but in powerful X-rays. When astronomers first mapped this X-ray emission, they expected to see a smooth, fuzzy cloud of energy. Instead, they found something that should be impossible: sharp, razor-thin edges slicing through the inferno. Scientists call these features cold fronts, though the name is a cosmic misnomer. The gas on one side of the edge is still unimaginably hot, millions of degrees, but it is distinctly colder and denser than the even more scorching, thin gas on the other side. Think of it like a weather front in our own atmosphere, where a mass of cold air bumps against warm air, creating a sharp dividing line. But in the near vacuum of intergalactic space, such a stark boundary should not last for more than a moment. Heat should flow from the hot side to the cold side almost instantly, smoothing out the temperature difference and erasing the sharp edge in a cosmic blink. Yet these cold fronts persist for hundreds of millions of years. They are stable, coherent structures etched into the cluster's atmosphere. The leading theory points to a violent past. These fronts are thought to be the result of sloshing motions, like wine swirling in a glass after a sudden jolt. A major merger between clusters billions of years ago would have sent powerful gravitational waves through the central gas, setting it into a slow, turbulent churn. In this model, the denser, colder gas from the core of one of the colliding clusters is still swirling around, shearing against the hotter, more diffuse gas. But the mystery is not the sloshing itself, it is the incredible sharpness of the boundary. What invisible force is acting like a perfect insulator, preventing heat from crossing the line and maintaining this cosmic cliff face? The leading suspect is magnetism. Weak magnetic fields, tangled throughout the plasma, could be draped along the surface of the cold front. These magnetic fields might be strong enough to suppress the microscopic collisions between particles that normally transfer heat, effectively creating an invisible blanket that keeps the two temperatures separate. Another possibility involves the complex physics of plasma itself. where turbulence and subtle pressure differences create a barrier. The existence of these long-lived, sharp cold fronts is a direct challenge. It tells us that our models of how matter behaves in the most extreme environments are still incomplete. We are witnessing a cosmic contradiction, a perfect, enduring edge in a place where chaos should reign supreme. What other invisible barriers and silent laws are governing the behavior of this seemingly formless void? While the cluster's hot gas glows in X-rays, a different kind of energy radiates in the shadows. Powerful infrared telescopes have pinpointed strange, brilliant spots scattered across Hercules, sources of intense heat that do not match any known celestial object. These unidentified infrared emitters are cosmic anomalies, shining with a light that is both powerful and deeply puzzling. They are not the familiar glow of standard galaxies, nor do they align with the profiles of known stars. They are simply points of unexplained heat, and their very existence forces us to consider what bizarre processes could be at work. The reason they shine so brightly in the infrared part of the spectrum is a critical clue. Infrared light is essentially heat radiation, the kind of energy emitted by warm objects that are not hot enough to glow with visible light. For an object to be so luminous in the infrared, it must be producing a tremendous amount of energy, and then shrouding that energy in vast, dense clouds of cosmic dust. Think of a brilliant light bulb completely encased in thick, black wool. The visible light is trapped and absorbed, but the heat still radiates outward, warming the wool and making it glow. These emitters are the cosmic equivalent, their central engines hidden from our view, their power revealed only by the warmth of their dusty shrouds. So what is the hidden engine inside? One compelling possibility is a dust-obscured supernova, a stellar explosion of unprecedented scale. A normal supernova blasts its material into space, creating a brilliant flash of visible light. But if the dying star was already surrounded by an immense, opaque cocoon of dust, the visible light would be completely absorbed. The energy, however, would heat the dust to incredible temperatures, causing it to blaze in the infrared for years or even decades. Another, more sustained explanation points to an exotic type of active galactic nucleus, or a GN. This is the supermassive black hole at a galaxy's center, but one that is feeding at a ferocious rate. As vast amounts of gas and dust spiral inward, the material heats up and should glow across the electromagnetic spectrum. Yet if the black hole is buried under a particularly thick, donut-shaped ring of dust, the visible and ultraviolet light is blocked. Only the infrared radiation, emitted by the warm dust itself, can escape, creating a brilliant infrared beacon with no visible counterpart. The mystery deepens because these objects seem to be outliers, even for these exotic categories. Their infrared brightness is extreme, pushing the limits of our models. Could they represent a brief, violent phase in a galaxy's life, a period of hyper-obscured growth that we have rarely witnessed? Or are we seeing an entirely new class of object, one where the rules of energy production and obscuration are fundamentally different? These unidentified emitters are more than just hidden lights. They are proof that our census of the cosmos is still incomplete, and that some of the most energetic events in the universe are happening in the darkest, most secretive corners. The brilliant infrared emitters are not the only cosmic rule breakers here. Among the countless galaxies swirling within Hercules, a select few stand out for their baffling proportions. These are the ultra-massive galaxies, collections of stars that rival the largest known in the universe, yet they are crammed into a shockingly small volume of space. They possess the weight of giants, but are trapped within the bodies of dwarfs. This is the galaxy size paradox, a direct challenge to our understanding of how galaxies evolve. In the quieter suburbs of the cosmos, a galaxy with this much mass would be expected to have a vast, sprawling disk, its stars distributed across hundreds of thousands of light years. But in the dense, urban core of Hercules, these behemoths are incredibly compact, their stars packed into a tight, brilliant sphere. How do they become so dense? The cluster's punishing environment provides two brutal, yet compelling, explanations. The first is a story of starvation and stifled growth. A galaxy grows in size not just by creating new stars, but by accreting vast clouds of gas and even swallowing smaller satellite galaxies. This process builds out its outer reaches, stretching it into the grand spirals we often see. In the heart of Hercules, however, this growth is violently suppressed. The superheated plasma that fills the space between galaxies acts as a barrier, preventing a massive galaxy from pulling in the fresh gas it needs to expand. Furthermore, the high-speed galactic traffic makes it difficult to capture and peacefully merge with smaller neighbors. The galaxy is left with all its immense mass, but no way to grow a larger body, forever trapped in its compact state. The second theory is even more dramatic. It suggests these galaxies were not always so small, but have been systematically shrunk over billions of years. This process is known as tidal stripping. Imagine a massive galaxy on a long, elliptical orbit through the cluster's core. Each time it swings through the dense central region, the combined gravitational pull of every other galaxy and all the dark matter tugs at its outermost stars. It is a relentless, cosmic sandblasting. Over countless orbits, the galaxy's faint, extended halo of stars is gradually peeled away, stripped from its grasp, and flung into the intergalactic void to form those faint tidal streams we discussed earlier. What remains is just the galaxy's dense, central core, the part that was gravitationally bound too tightly to be stolen. The galaxy loses its outer identity, becoming a compact relic of its former self. This leads to a profound question. Are we looking at galaxies that never grew up? Or are we seeing the stripped-down corpses of galaxies that were once far larger? The answer likely involves both narratives, a testament to the cluster's power to both stunt growth and dismantle giants. These compact powerhouses are a direct physical manifestation of the Hercules cluster's influence, a permanent record of the cosmic forces that can compress entire worlds into a fraction of the space they were meant to occupy. This faint, pervasive glow is the ghost of the cluster's violent past. A delicate, diffuse light permeates the spaces between the brilliant galaxies of Hercules, a cosmic fog made from billions of orphan stars. These stars do not belong to any galaxy. They were ripped from their homes during the gravitational encounters and collisions that have shaped the cluster over billions of years, and now they drift forever in the intergalactic void. Their collective light is incredibly faint, 1,000 times dimmer than the darkest night sky visible from Earth. To even detect this feeble glow requires meticulous effort, using the most powerful telescopes to take extremely long exposures while carefully subtracting the light from every known star, galaxy, and even the glow of our own atmosphere. It is like trying to hear a whisper in a roaring stadium. The pattern of this light, however, is a historical record. The way these stars are distributed across the cluster tells a vivid story of its assembly. If the diffuse light is smooth and evenly spread, it suggests an ancient, well-mixed history of many small galactic mergers. But if it is clumpy, concentrated in great streams and clouds, it points to more recent, violent collisions between large galaxies, their stellar debris not yet having time to settle. In Hercules, the light shows a complex structure, a turbulent map of ancient violence. The true enigma, however, is its sheer brightness. The total amount of this intracluster light is significantly higher than many computer simulations predicted. According to our best models of how clusters form, there should not be quite so many stars floating freely in the darkness. This forces a re-evaluation of the cluster's history. Perhaps the Hercules cluster experienced an unusually violent and chaotic youth, with a higher rate of galactic cannibalism than we thought. Or maybe the galaxies that were torn apart were inherently different, richer in loosely bound stars and their outer halos, making them easier to strip away. This excess of ghost light implies that the process of building a galaxy cluster is even more destructive than we imagined, leaving behind a far larger population of stellar orphans. These lost stars are more than just a faint glow. They are a direct measure of the chaos required to build a cosmic metropolis. What does it mean that so much of a cluster's light comes from stars that belong to no one? A galaxy in the Hercules cluster is caught in a cosmic limbo, glowing with a strange greenish hue that marks it as a celestial paradox. This is the Green Valley Galaxy, a world trapped between a vibrant, star-forming blue and a silent, aging red. It is neither fully alive nor completely dead, and its very existence challenges our models of galactic life cycles. What force could press pause on the evolution of an entire galaxy? The answer lies in the brutal environment surrounding it. In the open fields of the universe, galaxies often follow a predictable path. They are born blue, blazing with the light of young, hot stars, and they gradually turn red as their star-forming fuel is depleted and their stellar populations age. The Green Valley is the brief transitional phase between these two states, a period that should last only a few 100 million years, a mere blink in cosmic time. Yet this galaxy seems to be stuck, its transition unnaturally prolonged. The prime suspect is the cluster itself, acting as a cosmic saboteur. The galaxy is likely experiencing a process known as strangulation. As it orbits within the dense core of Hercules, its supply of fresh, cold gas from the intergalactic medium has been severed. The cluster's immense gravity and the scorching heat of the intracluster plasma prevent new fuel from falling in. The galaxy is now running on fumes, slowly consuming the last of its internal gas reserves. But why hasn't it simply used up this fuel and faded to red? The stalling may be due to a delicate, tragic balance. The remaining gas reservoirs could be just enough to support a trickle of star formation, but not enough to create the brilliant blue bursts of its youth. It is like a car engine, sputtering on the last drops in the tank, moving forward in fits and starts, but unable to regain full power. Alternatively, the galaxy might be undergoing a more violent, external intervention. Perhaps it recently experienced a high-speed encounter with another galaxy, or a blast of ram pressure from the cluster's hot gas, an event that did not strip all its gas away, but instead shock compressed the remaining fuel. This compression could have triggered a final, brief burst of star formation that used up just enough gas to leave it stranded, unable to continue but not yet fully extinguished. This galactic standstill offers a rare and critical window. By studying this single, stalled object, astronomers are witnessing a pivotal moment in a galaxy's life, a moment that is usually fleeting. Its prolonged pause forces us to ask whether the Green Valley is a simple transition for all galaxies, or if in some environments it can become a permanent state, a fate dictated not by internal clocks, but by the crushing influence of a metropolis that will not let its inhabitants live or die in peace. Even the ancient star clusters of Hercules refuse to follow the rules. Orbiting its massive galaxies are globular clusters that shine with an impossible brilliance, far outshining any such objects found around our own Milky Way. These are the overluminous globular clusters, and their existence forces a difficult question. Are we looking at a new class of cosmic object, or merely the ghostly remnants of ancient destruction? A typical globular cluster is a dense, spherical collection of up to 1 million ancient stars, all bound together by gravity. They are cosmic fossils, thought to have formed in the universe's chaotic infancy. The ones in Hercules, however, are in a league of their own. They are tens, sometimes hundreds of times more massive and luminous than their ordinary counterparts. Their sheer brightness places them in a strange category, blurring the line between a star cluster and a miniature galaxy. So what created these stellar powerhouses? One compelling theory is that they are not clusters at all, but the stripped nuclei of devoured dwarf galaxies. Picture a small galaxy falling into the gravitational well of a giant. As it swings past, the immense tidal forces rip it apart. The galaxy's outer stars are stripped away, joining the faint intracluster light, but its dense, central core, its nucleus resists dissolution. This surviving core, now adrift and orbiting the larger galaxy, would look exactly like an impossibly bright globular cluster. It is not a born cluster, but the orphaned heart of a devoured system. Another possibility is that they are the products of direct mergers. In the dense environment of the Hercules cluster, globular clusters themselves could have collided and merged, piling up their stars into a single, supersized object. This would be a relatively rare event, but in a place as crowded and violent as Hercules, rare events become probable. A third, more exotic idea is that these are genuine superclusters, objects that formed from unusually massive and dense clouds of gas in the early universe, creating a behemoth from the very start. Each explanation challenges our standard models in a different way. If they are stripped nuclei, it means our census of globular clusters is contaminated with galactic corpses, forcing us to reinterpret the entire archaeological record of galaxy formation. If they are merged clusters, it implies a dynamic and interactive life for these ancient objects that we never knew existed. Their overluminous nature is a direct result of the cluster's punishing density, an environment that can forge stellar giants through relentless collision and cannibalism. These brilliant clusters are more than just anomalies. They are evidence that even the oldest, most stable-looking structures in the universe have violent and complex histories, their true origins written in a light almost too bright to believe. Even the most powerful forces in the cosmos can be bent to the will of their environment. One galaxy within the Hercules cluster fires a pair of relativistic jets, colossal beams of energy and particles that scream into space at nearly the speed of light from its central supermassive black hole. These jets are cosmic blowtorches, capable of shaping entire galaxies, yet one of them is not shooting straight. It is violently bent, curving away from its original path like a stream of water from a hose hitting an invisible wall. This distorted jet is a direct result of the galaxy's high-speed motion through the cluster. The galaxy is not stationary. It is racing through the superheated, thin plasma that fills the space between galaxies. As it moves, the jet plows into this intracluster medium, a ghostly but substantial fog of charged particles. The resistance from this fog is immense, creating a powerful wind that pushes against the jet, forcing it to sweep backward and creating a spectacular curve. This distortion is more than just a cosmic oddity. It is a natural barometer for the cluster's most elusive component. By measuring the precise angle of the bend, astronomers can calculate the density and pressure of this invisible gas. It is like watching a flag fluttering in a strong wind. The shape of the flag tells you about the force of the wind you cannot see. The sharper the bend, the denser and more resistant the medium must be. This single, warped jet provides a direct measurement of the conditions in the seemingly empty intergalactic space, revealing it to be a dynamic and forceful environment. But the story does not end with gas pressure. The jet itself is a probe for another invisible force. The radio waves it emits are polarized, meaning their electromagnetic waves are aligned in a specific direction. As these waves travel through the cluster, The weak but pervasive magnetic fields tangled within the plasma twist this polarization, a phenomenon known as Faraday rotation. By analyzing how much the polarization has been twisted, scientists can map the strength and structure of these cosmic magnetic fields. This bent jet is therefore a unique and powerful tool. It simultaneously reveals the density of the scorching gas and the architecture of the invisible magnetic fields that are woven through it. It shows us that the space between galaxies is not a passive void, but an active, structured medium with its own weather and forces, capable of deflecting some of the most energetic phenomena in the universe. What other invisible currents and fields are silently guiding the evolution of this cosmic metropolis? Our census of the Hercules Cluster reveals a profound and unsettling absence. Where there should be thousands of tiny, faint dwarf galaxies swarming around the giants like bees around a hive, we see only a handful. This is the missing dwarf galaxy problem, a cosmological crisis that has persisted for decades. The most powerful computer simulations of our universe, based on the prevailing model of dark matter and gravity, consistently predict that vast halos of dark matter should have condensed in the early cosmos. Each of these halos should have pulled in enough ordinary gas to form a small galaxy, resulting in a cosmos teeming with dwarfs. Yet when we look at Hercules and other clusters, the numbers simply do not add up. We are missing more than 90% of the expected population. So where did they all go? One possibility is that our understanding of dark matter itself is flawed. Perhaps dark matter particles interact with each other in ways we have not accounted for, preventing the smallest halos from ever forming stars, leaving them completely dark and invisible. Another, more observational, solution is that many of these dwarfs do exist, but they are simply too faint for our current telescopes to detect. They could be so devoid of stars, or their stars so spread out, that their light is lost in the glow of the cluster itself. It is like trying to spot a single, dim candle from miles away while standing in front of a massive, brilliant searchlight. The most violent explanation, however, is that the cluster environment is a galactic slaughterhouse. As dwarf galaxies repeatedly orbit through the dense core over billions of years, they are subjected to relentless gravitational stresses and the scorching pressure of the intracluster gas. This brutal treatment could have systematically torn them apart, stripping away their gas and dispersing their stars, effectively erasing them from the visible cosmos and adding their substance to the sea of intracluster light. Their missing numbers are a ghostly testament to this destruction. This leaves us with a haunting question. Is the universe not building as many small galaxies as we thought? Or is Hercules, in its immense and violent power, simply a much more efficient destroyer than we ever imagined? Deep within the cluster's fiery core, a cosmic contradiction defies the laws of thermodynamics. Astronomers have discovered a dense cloud of cold gas, a frigid island adrift in a sea of plasma, burning at millions of degrees. This cloud is cooling at a ferocious rate, far faster than any model predicted. The physics seems straightforward. In the extreme density of the cluster center, the hot gas should radiate its heat away as X-rays, cool down, and then flow inward in a steady river toward the central galaxy. This is the classic cooling flow model, a process that should fuel incredible bursts of new star formation, raining fresh material down onto the waiting galaxy below. But here is the mystery. The gas is cooling, but that rain of new stars never seems to arrive. It is as if the cloud is being chilled, but something is preventing it from falling. This is the heart of the cooling flow problem, a paradox that has puzzled astrophysicists for decades. Where is all that cold gas going? The leading solution involves a cosmic thermostat, a feedback mechanism so precise it borders on artistry. The source of this regulation is the supermassive black hole at the galaxy's center, its active galactic nucleus, or a GN. When the cooling gas begins to flow inward, some of it inevitably feeds the black hole. This meal does not go quietly. The black hole responds with a ferocious outburst, pumping immense energy back into the surrounding gas through powerful jets and intense radiation. This AGN feedback acts like a giant blowtorch, reheating the cooling gas, halting its collapse, and preventing a runaway starburst. The system exists in a delicate balance, a cycle of cooling and heating that prevents the galaxy from either freezing over or burning out of control. Yet in Hercules, the cooling is so rapid, it seems to be testing the limits of this balance. Is the black hole's feedback just enough to stop the rain, but not enough to completely disperse the cloud? Or are we witnessing a brief, unstable phase in this cosmic dance, a moment where the thermostat is struggling to keep up? This single, rapidly cooling cloud is a live demonstration of one of the most important regulatory processes in the universe, a battle between fire and ice on a scale so vast it governs the life and death of galaxies. This lopsided cosmic city tells a story of its violent origins. The galaxies within the Hercules Cluster are not scattered evenly, but form a distinctly elongated and asymmetric structure, a shape that speaks of immense, unfinished forces. If the cluster were a calm, settled system in perfect equilibrium, gravity would have long since smoothed it into a more symmetrical, roundish shape, like a drop of water in space. Its continued lopsidedness is a clear sign that it is still dynamically young, a system still reeling from a colossal impact. The most likely culprit is a recent major merger, a cosmic car crash involving two smaller clusters that slammed together. The evidence is written in the skewed distribution of its galactic inhabitants. When these massive structures collided, they did not simply combine into a neat sphere. Instead, they passed through each other, their dark matter halos and galaxies interacting in a complex gravitational dance that left the entire system stretched out and off balance. The galaxies are like debris scattered after an explosion, their pattern preserving the direction and violence of the initial impact. This asymmetry is not permanent. Over hundreds of millions of years, the relentless pull of gravity will eventually work to erase this lopsidedness, tugging the wandering galaxies back toward a common center and smoothing the cluster into a more relaxed and symmetrical form. The fact that we can still see this pronounced elongation means the merger was a relatively recent event in cosmic terms. We are catching the Hercules Cluster at a special moment, witnessing the aftermath of the crash before the cosmic cleanup crew has finished its work. This raises a profound question about the nature of such colossal structures. Are galaxy clusters ever truly finished and at rest, or are they constantly being reshaped by new collisions, forever young and turbulent in the vast flow of cosmic time? At the very heart of this turbulent metropolis sits a ruler of unexpected silence. The central galaxy of the Hercules Cluster is a colossal giant, containing the mass of trillions of suns, yet its core is strangely, profoundly quiet. In other similar clusters, the central galaxy is often a blazing beacon, its supermassive black hole in a hyperactive state, devouring matter and spewing out enough energy to outshine every star in its host. This active galactic nucleus, or a GN, acts as a cosmic volcano, regulating the entire cluster's climate. But here, the volcano is dormant. Why is this titan so still, and what does its silence mean for the cosmic city it governs? This dormancy presents a fascinating puzzle. An active galactic nucleus is powered by accretion, the process of a black hole pulling in vast quantities of gas and dust. As this material spirals inward, it heats to incredible temperatures, glowing brilliantly and often powering colossal jets. For the Hercules central galaxy to be so quiet the flow of fuel onto its black hole must have been choked off. The question is, how the cluster's violent merger history may hold the key. The same colossal collision that created the radio halo and the cold fronts could have also disrupted the delicate mechanisms that feed the central beast. The sloshing motions of hot gas might have pushed the fuel reservoirs just out of reach, or the gravitational turmoil may have stabilized the gas, preventing it from falling inward. It is like a feast laid out on a table that is constantly being jostled, keeping the hungry guest from getting a steady meal. This quiet core has dramatic consequences for the entire cluster. Without the frequent, powerful outbursts from an active AGN, there is no central energy source to heat the surrounding gas and prevent it from cooling. This brings us directly back to the mystery of the rapidly cooling cloud. In a way, the two phenomena are linked. The dormant black hole is not providing the feedback needed to act as a thermostat, which may be why the cold gas cloud can exist and cool so efficiently. The balance of power has shifted. Instead of being governed by the cyclical outbursts of a central engine, the core of Hercules is likely dominated by the broader, more chaotic effects of its merger-shaped environment. The gravitational tides, the sloshing gas, and the high-speed galactic traffic. This silence is not peaceful. It is the quiet of a system waiting for a new equilibrium, or perhaps building toward a future cataclysm. This leads to an inevitable and thrilling question. Is this silence permanent, or is the galaxy simply gathering its strength? The immense reservoir of cold gas hovering nearby represents a colossal potential fuel source. It is entirely possible that we are witnessing a calm before an unimaginable storm. If even a fraction of that cooling gas were to suddenly fall onto the dormant black hole, it could ignite one of the most spectacular outbursts ever seen, a rebirth of the cosmic volcano that would reshape the cluster core for eons to come. The silent giant at the heart of Hercules may not be sleeping. It may simply be holding its breath. The silent giant at the heart of Hercules may be holding its breath, but the space around it is crackling with invisible bullets. An unexplained flood of high-energy cosmic rays appears to be streaming from the direction of the cluster itself. These are not rays of light, but atomic nuclei, mostly protons, accelerated to nearly the speed of light, carrying energies far beyond anything our most powerful particle colliders on Earth can produce. They are the universe's natural artillery, and Hercules seems to be firing more than its fair share. The data comes from vast observatories on the ground, which do not detect the particles directly. Instead, they see the enormous showers of secondary particles created when a single cosmic ray slams into the upper atmosphere, a cascade of energy that spreads for miles. By tracing these showers back to their approximate origin in the sky, scientists have noticed a statistical excess, a consistent hotspot pointing back toward the Hercules cluster. The source of this relentless barrage, however, remains completely hidden. One of the prime suspects is a hidden population of supernova remnants. When a massive star explodes, the expanding shockwave can act as a natural particle accelerator, boosting protons and other nuclei to these incredible energies. In a dense environment like Hercules, there could be thousands of these remnants, their visible light obscured by dust, but their invisible particle output combining into a powerful, diffuse signal. Yet, the sheer energy of some of these cosmic rays pushes the limits of what a standard supernova remnant is thought capable of producing. This leads to a more exotic and tantalizing possibility. The excess could be a signature of dark matter annihilation. If dark matter is made of theoretical particles that are their own antimatter counterparts, then when two of them collide, they could annihilate in a flash of energy, producing a spray of standard particles, including the high-energy protons we detect as cosmic rays. The dense core of the Hercules cluster with its immense concentration of dark matter, would be the perfect furnace for this process. The challenge is one of cosmic forensics. Pinpointing the exact origin of a cosmic ray is nearly impossible. Because these particles are charged, their paths are bent and scrambled by the magnetic fields that fill interstellar and intergalactic space. By the time one reaches us, it is like finding a bullet at a crime, seen without any clear line of sight to the gun that fired it. We know the general direction of the barrage, but the specific sniper's nest could be anywhere within that vast metropolis of galaxies and dark matter. This excess is a ghostly signal from a hidden war, a bombardment of particles that could be the fallout from countless stellar explosions, or something far more profound, the first indirect glimpse of dark matter, revealing its presence not through gravity, but through its own self-destruction. A single point of light flared into existence where there was nothing, and then it was gone. This was no supernova, no known stellar explosion, but a transient optical source of utter mystery. In a series of detailed observations, astronomers watched a pinpoint of visible light within the Hercules Cluster brighten dramatically over a short period, only to fade completely from view, never to be seen again. The immediate task was one of elimination, a process of cosmic deduction to identify what this flare could not be. A typical supernova, the violent death of a massive star, was the first and most obvious candidate. But this flash was all wrong. It did not follow the characteristic light curve of a supernova, which rises to a peak over weeks and then decays slowly over months. This event was too fast, its behavior too erratic. Furthermore, supernova leave behind expanding shells of gas or dense stellar remnants, a visible ghost at the site of the explosion. When telescopes searched that exact location after the flare vanished, they found nothing. No nebula, no neutron star, just the same empty darkness as before. Other known transients were ruled out one by one. It was not a gamma ray burst afterglow, as there was no corresponding high-energy signal. It was not a tidal disruption event, where a star is shredded by a black hole, because those produce sustained bright emissions for much longer. This left scientists with a profound and thrilling emptiness, a hole in their understanding where an explanation should be. The most tantalizing possibility is that this fleeting light was a glimpse of something entirely new, a previously unknown astrophysical event. Perhaps it was the signature of a star being consumed by an exotic, intermediate mass black hole in a way we have never witnessed. Or maybe it was the flash from a collision between two incredibly dense objects, like neutron stars and white dwarfs, occurring in a unique configuration. This single, vanished point of light is a powerful reminder that our maps of the cosmos are still incomplete. For one brief moment, the universe revealed a new kind of spark in the darkness, a secret it has not yet fully shared, leaving us to wonder what other fleeting wonders occur in the vastness of space, unseen and unexplained. Even the silent spaces between the stars are humming with a secret tune. The most profound discovery from the Hercules Cluster might not be something we can see or hear, but something we can feel in the very fabric of reality. Astronomers now suspect that the cluster's violent past of colliding galaxies and merging supermassive black holes has contributed to a faint, universe-wide hum, a persistent ripple in space-time known as the gravitational wave background. This is not the loud, singular chirp of two stellar mass black holes merging, a signal that lasts for mere seconds. This is a chorus, a deep, low-frequency rumble built from the combined echoes of countless monstrous collisions that have occurred across cosmic time. To detect this whisper, scientists use the universe's most precise timekeepers, pulsars. These are the rapidly spinning cores of dead stars, acting as cosmic lighthouses that flash with metronomic regularity. By monitoring networks of these pulsars across our galaxy with radio telescopes, researchers create a pulsar timing array. The concept is one of breathtaking precision. As a gravitational wave, a ripple in space itself, passes between Earth and a pulsar, it minutely stretches and compresses the distance the light has to travel. This causes the otherwise perfectly regular pulse of light to arrive at our telescopes just a fraction of a second, early or late. By carefully tracking the correlated timing deviations across many different pulsars, astronomers can piece together the presence of the background hum. A confirmed signal would be the ultimate testimony to the Hercules Cluster's most cataclysmic history. It would tell us, directly and unequivocally, that the supermassive black holes we now see sitting quietly at the centers of giant galaxies did not form in isolation. They grew through a violent, hierarchical process of collision and merger, a cosmic dance of titans that shook the universe. Each detected ripple would be a fossilized imprint of an ancient embrace between black holes millions of times more massive than our sun. This hum is the sound of the cosmos building its greatest structures, a low growl from an era when galaxies were constantly crashing together, their central beasts spiraling inward and merging in a final gravitational shout. What stories of ancient violence are written in these quiet ripples, and what will they ultimately reveal about the fate of all the great clusters that fill the darkness? From missing dark matter to ghostly radio whispers, these 25 mysteries are more than just cosmic oddities. They are the very frontiers of our understanding, a collection of profound challenges that force us to question the fundamental rules of physics. Each unexplained phenomenon, from the Hercules-Corona Borealis Great Wall that defies the universe's smoothness to the silent, dormant giant at the cluster's heart, represents a crack in the foundation of our knowledge. The phantom rings of dark matter, the strangely bent jets, and the flood of cosmic rays all point toward a cosmos far more complex and dynamic than we ever dreamed. This cluster is a cosmic puzzle box, and every time we solve one piece, two more appear, each more baffling than the last. These are not dead ends, but invitations. They are calls to look deeper, to build better telescopes, and to dream bigger theories. The universe is not finished revealing its secrets, and the Hercules Cluster remains one of its most eloquent teachers. So we turn the question to you: of all these profound mysteries, which one captures your imagination the most? Is it the galaxy that exists without its dark matter, the possibility of a hidden multiverse tugging at everything we see, or the silent hum of gravitational waves from ancient black hole mergers? Share your thoughts, and never stop looking up at the stars with wonder. The next great discovery is waiting.